there is a machine that changed the world. Not the internet. Not the transistor. Not the microchip. A machine that was designed in London in the 1830s, before electricity powered a single home, before the telephone existed, before anyone had spoken the word computer in the way we understand it today. The man behind it was a mathematician named Charles Babbage. His name appears in textbooks. His portrait hangs in institutions. His story is told, retold, celebrated. But there was someone else in that room. Someone who understood the machine more deeply than its creator. Someone who wrote, in extraordinary detail, what it could truly become. Not just a calculator, but something capable of reason itself. Her name does not appear in most textbooks. For nearly a century, her contribution was reduced to a footnote. Then erased entirely. Then, when it was finally rediscovered, historians argued for decades about whether she had truly understood what she wrote, or simply copied it from someone else. Her name was Ada Lovelace. She died at 36. And the document she left behind described the future of computing more than 100 years before it arrived. This is her story. Augusta Ada Byron was born on December 10, 1815, in London, the only legitimate child of the poet Lord Byron, one of the most famous and scandalous men in England. Her father left when she was 5 weeks old. He never came back. Historical records suggest that Ada's mother and Isabella Milbanke, a woman trained in mathematics, known in her social circle as the Princess of Parallelograms, made a deliberate decision after the separation. She was terrified. Not of poverty. Not of scandal, though there was plenty of that. She was terrified that her daughter would inherit her father's madness. Lord Byron was brilliant, reckless, emotionally volatile. He had affairs, debts, feuds. He wrote poetry that made women weep and men furious. He died in Greece at 36, the same age Ada would die, decades later, fighting in a war that wasn't his. And Isabella's solution was precise and, by any Victorian standard, extreme. Ada would study science, mathematics, logic, the rational disciplines. Poetry was forbidden. Imagination was to be controlled. Emotion was to be suppressed through rigorous intellectual structure. It didn't work, not in the way her mother intended. What it produced instead was something far more dangerous. A young woman with a poet's instinct for pattern and metaphor, trained with the analytical precision of a mathematician. By 12, Ada was designing mechanical flying machines, studying bird anatomy, calculating wing-to-body ratios, drafting specifications. She called the project Flyology. By 17, she had recovered from a partial paralysis that kept her bedridden for years, and emerged from it with a mind sharpened, not dulled. By 18, she was introduced to Charles Babbage at a dinner party in London. And everything changed. Charles Babbage was 51 years old when Ada Lovelace walked into his drawing room and saw it. The difference engine. A mechanical calculating machine, partially constructed, gleaming on a demonstration table. It was designed to compute mathematical tables, the kind used by navigators, engineers, and astronomers, automatically, without human error. Most visitors admired it politely and moved on. Ada stood there and stared. According to surviving accounts from those present, she asked Babbage questions no one else had thought to ask. Not about how the gears moved. About what the machine meant. About what it could become. Babbage later wrote that she was the only person who had ever truly understood the difference engine on first encounter. But the difference engine was not what Babbage really wanted to build. What he wanted, what he had been secretly designing for years, was something far more ambitious. He called it the analytical engine. The difference between the two machines was not a matter of scale. It was a matter of kind. The difference engine could calculate. It followed a fixed mathematical procedure, start to finish. The analytical engine could be programmed. It had a mill, the processing unit, and a store, the memory. It could receive instructions on punched cards, a concept borrowed from the jacquard loom used in textile manufacturing. It could perform different operations depending on results. It could loop. It could branch. Some historians believe that if the analytical engine had been built in 1837, the history of human civilization would have been structurally different. It was never built. The British government withdrew funding. The engineering required was beyond what Victorian precision manufacturing could consistently deliver. Babbage spent the rest of his life, more than 30 more years, designing and redesigning it, arguing with engineers, fighting with government committees. But the idea existed. The blueprints existed. And in 1842, an Italian mathematician named Luigi Minabrea attended one of Babbage's lectures and wrote a technical description of the analytical engine in French. Babbage had no interest in translating it. Ada Lovelace did. What she produced was not a translation. It was the document that changed everything. It began as a straightforward task. In 1842, Charles Babbage asked Ada, by then Ada King, Countess of Lovelace, married with 3 children, to translate Minabrea's French article on the analytical engine into English for publication in a British scientific journal. The translation took 9 months. What she produced was more than twice the length of the original. Ada had added her own annotations, labeled alphabetically, from note A to note G. These notes did not merely explain the machine. They explored what it implied, what it could do, what it fundamentally was. Note G was the last, the longest, and the most significant. In it, Ada described, in precise step-by-step notation, how the analytical engine could be programmed to compute Bernoulli numbers, a complex sequence used in mathematics and physics. She laid out the sequence of operations, the variables, the logical flow. It was, according to the scholarly consensus that would emerge more than a century later, the first algorithm ever written for a machine. But Note G was not only a technical specification. It was also a philosophical argument. Ada wrote that the analytical engine had no power to originate anything. It could only do what it was instructed to do. It operated on relationships between objects. But those objects, she argued, did not have to be numbers. They could be musical notes. They could be letters. They could be symbols of any kind, as long as their fundamental relationships were definable. She was describing, in 1843, the theoretical basis of what we now call general-purpose computing. She also wrote something that computer scientists would argue about for the next 150 years. The analytical engine has no power of originating anything. It can only do what we know how to order it to perform. Alan Turing would directly engage with this claim in 1950, in his paper Computing Machinery and Intelligence, calling it Lady Lovelace's objection. Ada Lovelace died 7 years after writing Note G. She was 36 years old. The notes were published. The machine was never built. And the world moved on. Here is what happened to Ada Lovelace's legacy in the decades that followed her death. Nothing. The notes were published in 1843 in Taylor's Scientific Memoirs. They were attributed to AAL, her initials, not her name. Victorian convention made it unusual, and often professionally dangerous, for women to publish scientific work under their own names. Babbage continued to work on the analytical engine until his death in 1871. He referenced Ada's contributions privately, in letters and memoirs. But the machine was never built, and without a working prototype, the notes had no context to make them famous. Ada had died in 1852 of uterine cancer. Her husband, at her request, buried her beside her father, Lord Byron, in the Byron family vault in Nottinghamshire. In the years that followed, the few scholars who encountered her work treated it carefully. Some praised it. Some questioned it. And then, gradually, as computing moved forward in the 20th century, not through mechanical gears but through vacuum tubes and transistors, Ada's name disappeared from the conversation almost entirely. When historians and engineers began constructing the origin story of the computer in the 1940s and 1950s, they looked to Babbage, to Turing, to von Neumann. They found Ada's notes eventually. But the question asked was not what did she contribute. It was a more corrosive one. How much of it was really hers? Some scholars argued that Babbage had done most of the technical work in Note G, that Ada had merely transcribed his ideas. One 1970s biographer described her as a minor figure whose importance had been inflated. Others suggested the notes showed brilliance, but brilliance at explaining someone else's thought, not at originating her own. The exact division of intellectual credit between Ada Lovelace and Charles Babbage remains a matter of historical debate. But the letters survive. In her correspondence with Babbage during the 9 months of work, Ada pushes back. She corrects him. She proposes ideas he hadn't considered. She identifies errors in calculations. She asks questions he cannot immediately answer. In one letter, she writes something that does not read like an assistant taking dictation. "I am working very hard for you, like the devil in fact." Between Ada Lovelace's death in 1852 and the construction of the first electronic computers in the 1940s, nearly 100 years passed. In those 100 years, the analytical engine was never built. Babbage's blueprints remained in archives. Ada's annotated translations sat in libraries, consulted occasionally by historians of mathematics, largely unknown to the engineers building the actual future. The ENIAC, completed in 1945 at the University of Pennsylvania, is often described as the first general-purpose electronic computer. It was programmed in its early days, almost entirely by a team of 6 women: Kay McNulty, Betty Jennings, Betty Snyder, Marlon Westkoff, Fran Bilas, and Ruth Lichterman, whose contributions would also go largely unrecognized for decades. The pattern was not coincidental. In the history of computing's foundational era, women were frequently doing the work while men received the institutional credit. Ada Lovelace had experienced a version of this a century earlier. The women of ENIAC would experience it again. But something was changing. In 1953, 110 years after Ada's notes were first published, Bertram Bowden included a reprint of her translation and annotations in his book Faster Than Thought, a symposium on digital computing machines. It was the first time Ada Lovelace's work had been reprinted in over a century. Bowden described the notes as remarkable. He drew explicit connections between what Ada had described and what modern computers were now doing. Historians began to look again. What they found surprised them. The formal rediscovery of Ada Lovelace as a significant figure in the history of computing happened gradually, across several decades, through the work of multiple researchers in different countries. But there was a turning point. In the 1970s, the United States Department of Defense was undertaking one of the most complex software engineering projects in history. The American military operated hundreds of different computer systems, written in dozens of incompatible programming languages. The result was chaos: programs that couldn't communicate, systems that couldn't share data, enormous costs in translation and maintenance. The solution was to create a single, unified, high-level programming language that could run across all military systems. The project took years. The language that emerged from it was designed to handle the full complexity of real-time embedded systems: aircraft, missiles, radar, logistics. It was powerful, disciplined, and demanding. In 1980, the Department of Defense officially named it. They called it Ada. The choice was deliberate. The language was named in honor of Ada Lovelace, whose notes had described, in 1843, the conceptual principles underlying exactly the kind of programmable, general-purpose computation the language was designed to perform. It was a formal, institutional acknowledgement that something important had been overlooked. Around the same time, historians of computing were re-examining Ada's notes with fresh attention. The scholarly debate about her contributions, was she originator or transcriber, intensified. But the terms of the debate had shifted. Now the question was not whether she had contributed. It was how much. Some historians went further. They pointed out that Ada had described, in Note A of her annotations, a conceptual framework that prefigured the stored program architecture. That she had understood, better than Babbage himself, the philosophical difference between a calculating machine and a computing machine. That the question, can a machine think, which Alan Turing would pose in 1950 as a foundational problem of artificial intelligence, was already being explored, in different language, by Ada Lovelace in 1843. The exact cause of how much credit is historically appropriate remains, even today, a matter of scholarly discussion. But the notes themselves are not in dispute. They exist. They are precise. They are extraordinary. And they were written in 1843 by a 27-year-old woman who had been taught, from childhood, that imagination was dangerous. Every device you have used today ran on algorithms. The search that found your last answer. The feed that showed you the next video. The map that routed your last trip. The voice that answered your question. Algorithms. Step-by-step logical instructions, given to a machine, telling it how to transform an input into an output. The word existed before Ada Lovelace. The concept existed before Ada Lovelace. But the specific act of writing one, formally, precisely, for a machine that could theoretically execute it, begins, as far as historical records show, with Note G of Ada's annotations to Menabrea's memoir, published in 1843. That is not a sentiment. It is a technical assessment made by computer scientists in the 20th century, after examining the document in the context of what they now knew machines could do. Ada Lovelace did not live to see a computer run. She died before the telegraph was even widely understood. She wrote about a machine that was never built. And yet the questions she asked are still being asked. Can a machine originate thought? Or only execute instructions? Ada's answer, in 1843, was, only execute instructions. Turing's answer, in 1950, was, the question is more complicated than that. The answer in 2024 is, we still don't fully know. The programming language named in her honor was used for decades in aviation, missile guidance, and space exploration. Ada code ran in systems where errors were not acceptable, where a single logical mistake could mean catastrophic failure. It was the kind of work that demanded exactly what Ada had demonstrated in Note G: precision, structure, and a deep understanding of what a machine can and cannot do. She had no institution behind her. No university degree. No laboratory. No funding committee. She had 9 months, a set of annotations, and a mind that could hold poetry and mathematics in the same thought at the same time. That brain of mine, she once wrote to her mother, is something more than merely mortal, as time will show. She was right. It just took longer than she thought.